Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon, but it's kinda got to make you laugh to think that you can go all the way to the moon and back using something that's ultimately just an approximation. Everything in our universe seems perfect. There are laws governing the entire universe, but certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie? It's merely a construct of the human brain. This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down to find out what on earth is wrong with gravity. We need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. There's a problem with Newton's theory of gravity, and that's that it just allows us to predict how things move under its influence. It doesn't say anything about why gravity exists or even how it works. It just allows you to calculate things, and Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets, and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God. In the vast universe that surrounds us, there are mysteries waiting to be uncovered. Among these mysteries are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredible speed close to the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who's not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path forming a zigzag. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a longer diagonal path. Now here's where it gets interesting. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside, but since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. It's not just a concept. Experiments have confirmed these relativistic effects. For example, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens the door to a world where time is not a constant, where it can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the realization that the universe operates in ways far beyond our common experience. Einstein's special theory of relativity, introduced in 1905, eclipse of 1919 when Sir Arthur Eddington led an expedition to observe the bending of starlight by the sun's gravity. According to the theory, the sun's massive presence would curve the path of light from distant stars, making them appear slightly shifted from their usual positions. Eddington's observations matched Einstein's predictions, providing strong evidence for the curvature of spacetime. Another fascinating prediction of general relativity is the existence of black holes. These are regions of spacetime where gravity is so strong that nothing, not even light, can escape. The idea of black holes emerges naturally from the mathematics of general relativity. When a massive star undergoes gravitational collapse, it can create a singularity, a point of infinite density surrounded by an event horizon beyond which nothing can return. In recent years, we have gained direct evidence of black holes through observations of gravitational waves, which are ripples in the fabric of spacetime caused by the acceleration of massive objects. When two black holes merge, they create gravitational waves that propagate through the universe. The detection of these waves by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, has confirmed the existence of black holes and provided further support for general relativity. One of the more mind-bending aspects of general relativity is the concept of gravitational time dilation. Near massive objects, just as time slows down when we move at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer close to a massive object compared to someone farther away. This effect has been observed and measured. For example, precise atomic clocks placed at different altitudes show that time runs slightly faster at higher elevations where the gravitational pull is weaker. The implications of general relativity are not limited to extreme cosmic phenomena. They also play a crucial role in understanding the large-scale structure of the universe. The expansion of the universe, first observed by Edwin Hubble, is explained by the general theory of relativity. The theory describes how the fabric of spacetime itself can stretch and expand, carrying galaxies with it. The general theory of relativity has transformed our understanding of gravity and the cosmos. It reveals that gravity is not a mysterious force acting at a distance, but a consequence of the curvature of spacetime caused by massive objects. This elegant idea has been confirmed by numerous observations and experiments, from the bending of starlight to the detection of gravitational waves. The concept of gravitational time dilation further emphasizes the interplay between time and gravity. Einstein's theories have revolutionized our understanding of the universe, providing profound insights into the nature of reality. While they may not provide all the answers, they have opened new avenues of exploration and inquiry. Einstein's theories challenge us to think deeply about the fundamental nature of spacetime, time, and the universe itself. They suggest that our intuitive understanding of reality may be limited and that the cosmos operates in ways that defy our everyday experience. Theories like relativity remind us that scientific knowledge is a journey of discovery, where each breakthrough leads to new questions and deeper understanding. In conclusion, Newton's theory of gravity laid the foundation for understanding the mechanics of celestial motion, but it was Einstein's theories of relativity that revolutionized our understanding of gravity as a fundamental property of spacetime. The special theory of relativity introduced the concepts of time dilation and the constancy of the speed of light, challenging our notions of time and simultaneity. The general theory of relativity further advanced our understanding by describing gravity as the curvature of spacetime caused by mass and energy. This concept not only explained gravitational phenomena like the orbits of planets and the bending of light, but also predicted exotic phenomena such as black holes and gravitational waves, which have since been observed. Einstein's theories continue to inspire and guide scientists in their quest to understand the universe at both the largest and smallest scales. They have reshaped our view of the cosmos, revealing a universe where space and time are intertwined, and where the force of gravity is a manifestation of the geometry of spacetime itself. As we continue to explore and experiment, Einstein's theories remind us that the universe is full of mysteries waiting to be uncovered. Each new discovery brings us closer to unraveling the secrets of the cosmos and understanding our place within it. Albert Einstein's theories of relativity, introduced in the early 20th century, represent a profound shift in our understanding of the universe. The special theory of relativity, published in 1905, fundamentally altered concepts of time and space. One of its key tenets is the constancy of the speed of light, which remains the same for all observers, regardless of their motion. This concept challenged Newtonian mechanics, where time and space were considered absolute and separate entities. Special relativity also introduced the notion of time dilation, where time passes differently for observers in relative motion. This effect becomes more pronounced as velocities approach the speed of light. The famous twin paradox illustrates this. If one twin travels at near light speed while the other remains on Earth, the traveling twin will age slower, returning younger than the Earth-bound twin. Moreover, special relativity predicts length contraction, meaning objects moving at high speeds appear shorter along their direction of motion when observed from a stationary frame. This phenomenon has been experimentally validated and is crucial in understanding particle accelerators and cosmic ray collisions. Einstein's general theory of relativity, published in 1915, revolutionized our understanding of gravity. Unlike Newtonian gravity, which described it as a force acting at a distance between masses, general relativity portrays gravity as the curvature of spacetime caused by mass and energy. This curvature alters the paths of objects, including light, which appear to follow curved trajectories near massive bodies like stars and planets. The concept of spacetime in general relativity unifies space and time into a four-dimensional continuum where massive objects deform this fabric, much like placing a heavy ball on a stretched sheet. This curvature dictates how objects move through spacetime, explaining phenomena such as planetary orbits and the bending of starlight observed during solar eclipses. General relativity also predicts the existence of black holes, regions where gravity is so intense that nothing, not even light, can escape. These exotic objects have been indirectly observed through their gravitational effects on nearby stars and gas clouds, as well as through the detection of gravitational waves emitted when black holes merge. Gravitational waves themselves are a prediction of general relativity, confirming Einstein's theory that accelerating massive objects should create ripples in the fabric of spacetime. The first direct detection of gravitational waves in 2015 by the LIGO observatories marked a milestone in physics, opening a new era of gravitational wave astronomy. Furthermore, general relativity explains gravitational time dilation, where time runs slower in stronger gravitational fields. This has practical implications, such as the need to account for time differences in GPS satellites orbiting Earth, which experience slightly weaker gravity compared to the surface. Beyond its astrophysical implications, general relativity plays a crucial role in cosmology, describing the expansion of the universe and the formation of large-scale structures. The theory's equations provide insights into the nature of dark matter and dark energy, which dominate the universe's composition but remain mysterious. In conclusion, Einstein's theories of relativity have not only reshaped our understanding of fundamental physics, but also influenced diverse fields from astronomy to technology. They continue to inspire new research, pushing the boundaries of our knowledge and challenging our perceptions of space, time, and the cosmos itself. Albert Einstein's theories of relativity, particularly the special and general theories, have had profound implications across physics and astronomy, reshaping our understanding of fundamental concepts such as space, time, and gravity. The special theory of relativity revolutionized the way we perceive space and time. It introduced the idea that the speed of light is constant for all observers, regardless of their motion relative to the source of light. This constancy of light speed implies that time and space are not absolute but are intertwined in what Einstein termed spacetime. The theory also predicts phenomena such as time dilation and length contraction. Time dilation means that time passes differently for observers in motion relative to each other. Moving clocks run slower compared to stationary ones. Length contraction, on the other hand, suggests that objects moving at high velocities appear shorter in the direction of their motion when observed from a stationary frame. These predictions have been confirmed by numerous experiments involving particle accelerators and high-speed cosmic ray collisions, validating Einstein's theoretical framework. The general theory of relativity expanded on these ideas by presenting gravity not as a force acting at a distance, as described by Newtonian mechanics, but as the curvature of spacetime caused by the presence of mass and energy. According to general relativity, massive objects like stars and planets warp the fabric of spacetime around them, much like placing a heavy ball on a stretched rubber sheet. This curvature affects the paths of objects moving through spacetime, including the trajectory of light. For instance, during a solar eclipse in 1919, observations of starlight bending around the sun confirmed Einstein's predictions, providing strong evidence for the theory. General relativity also predicts the existence of black holes, regions where the gravitational pull is so intense that nothing, not even light, can escape from within a certain boundary called the event horizon. These predictions have been substantiated by observations of stars orbiting invisible companions, likely black holes, and by the detection of gravitational waves from merging black holes by instruments such as the LIGO and Virgo detectors. Gravitational waves themselves are a direct consequence of general relativity, representing ripples in the fabric of spacetime caused by accelerating massive objects. Their detection in 2015 marked a significant milestone in astrophysics, confirming Einstein's theory and opening a new era of gravitational wave astronomy. These waves provide a unique way to study violent events in the universe, such as the collisions of black holes and neutron stars, which emit gravitational waves that travel across vast cosmic distances. Moreover, general relativity's insights extend beyond astrophysics into cosmology, the study of the universe as a whole. The theory plays a crucial role in explaining the large-scale structure of the cosmos, including the expansion of the universe and the formation of galaxies and galaxy clusters. It has also contributed to our understanding of dark matter and dark energy, which together constitute the Einstein's theories of relativity, have had a profound impact on both theoretical physics and practical applications. Beyond revolutionizing our understanding of gravity, space, and time, they have stimulated further exploration and discovery across various scientific disciplines. One of the enduring legacies of Einstein's work is its influence on our understanding of the nature of the universe itself. The theories of relativity provided a unified framework that reconciled mechanics, special relativity, and gravitation, general relativity, under a single theoretical umbrella. This unified approach not only resolved inconsistencies between earlier theories but also laid the groundwork for modern theoretical physics. In practical terms, Einstein's theories have had significant implications for technologies such as Global Positioning System, GPS. The accuracy of GPS, which relies on precise timing signals from satellites, is enhanced by accounting for both special and general relativistic effects. Due to the differences in gravitational potential and the satellite's high orbital speeds relative to observers on Earth, clocks aboard GPS satellites experience time dilation compared to clocks on the ground. Without compensating for these relativistic effects, GPS systems would quickly become inaccurate, demonstrating the theory's relevance in everyday applications. Moreover, Einstein's theories continue to drive scientific research in fields ranging from cosmology to particle physics. They have provided critical insights into the behavior of matter and energy in extreme environments, such as near black holes and during the early moments of the universe. Observations of gravitational waves from merging black holes and neutron stars have not only confirmed key predictions of general relativity, but also opened up new avenues for studying the universe's most energetic events. In cosmology, general relativity plays a central role in our understanding of the universe's evolution. It describes how the distribution of matter and energy influences the curvature of spacetime, which in turn determines the large-scale structure of the cosmos. The theory's predictions have been borne out by observations of the cosmic microwave background radiation, galaxy clusters, and the overall expansion rate of the universe, corroborating our current understanding of cosmic history.